So yesterday we looked at single-step reactions for addition, elimination, and substitution. And through those three processes, we actually only made two functional groups. We made alcohols and we made amines. That means there are 6 functional groups that have to be covered today, and they're actually covered with 2 reactions. We're going to look at 3 reactions altogether, but we'll start with oxidation. So oxidation is when you form more bonds to an oxygen or less bonds to a hydrogen, and often both of those things are actually happening. So the starting material for oxidation are alcohols, and what we're going to turn them into is aldehydes and ketones. The aldehyde can actually even go one step further, and it can be made into a carboxylic acid, as we will see. So those are the 3 functional groups we can actually make through oxidation. So again, we start with the alcohol. We can turn it into an aldehyde, a ketone, and a carboxylic acid. What we're going to use is an oxidizing agent. So we just use the symbol O square brackets. I think the textbook uses O round brackets with a star. There's lots of different ways to symbolize an oxidizing agent. Basically, it's the thing that does this. Some examples of oxidizing agents are potassium permanganate, dichromate ions, and sulfuric acid. I can't think of anything else off the top of my head, but there's several different things that are considered oxidizing agents that help this process occur. Again, we're not going to identify what we're using. We're going to keep it simple, and we're going to just show O square brackets if we're oxidizing something. So again, we're going to start with an alcohol, and as soon as I see the oxidizing agent in here, what it's going to do is it's going to make a ketone. We don't actually have to show this process. When you get into advanced organic chemistry, if you go on in chemistry in university and you take like 3rd and 4th year, you'll show reactions, how they work on an electron level. But all we really need to know is that the action will happen right here. And what it will do is it will take that COH and that other H, and it's actually going to turn it into a carbonyl group. So let me show you what it ends up looking like. You'll notice that we got rid of the H that was next to the O. We got rid of the H on the bottom of that C, otherwise carbon would have too many bonds. We are not going to show the H, the 2 H's. We could show the 2 H's over here, but we generally don't because, again, this is the main product, and this is a little bit unknown. The reason why it's unknown is because we haven't identified our oxidizing agent, so it's possible that the H's would be combined with the oxidizing agent to make a totally different byproduct, and we don't really know, so we just sort of exclude it, and we just stick to our main product here, which is what our end goal was, to make a ketone, a double bonded O in the middle of a chain. So this is just our carbonyl group, which we've seen before, and it's in the middle of the chain. So this next reaction is a primary alcohol as the starting material. Again, whenever we see this oxidizing agent, it means that our focal point is going to be the carbon with the double bond, or with the OH, and it's going to make a double bonded O. So we've got our 3 carbons, and again, that COH becomes a double bonded O. We'll still need one of the H's on this carbon, because we need to have 4 bonds in total for carbon. But again, we don't show the byproduct of the H's. We lost 2 H's again. We don't show that because, again, we're not really sure what the oxidizing agent is. It could be combined with it in some way. So we're just going to show our main ingredient right here and our new carbonyl group. Because it's on the end of a chain, of course, this time we're making an aldehyde. Now, instead of starting with an alcohol, I'm starting with the aldehyde functional group. And when I have an aldehyde and I'm oxidizing, it turns it into a carboxylic acid. So I'm going to make a really small move here between the aldehyde and the carboxylic acid. So the oxygen to make the carboxylic acid would come from our oxidizing agent. Again, we're not going to show any sort of byproducts. That's not the important piece here. But we want to know that, again, an aldehyde becomes a carboxylic acid. We don't have to show how or the intricate details. We just have to know that this is what would happen. On to reaction number 5, which is condensation. And again, condensation makes 3 functional groups as well. This is, and you have previewed this when you did polymers, this is when 2 molecules form a single molecule and water is going to be eliminated. So you saw this more advanced version with polymers when it was happening on both ends of 2-sided sort of reactions, whereas condensation typically is just 2 ingredients, 2 reactants, making a larger product plus water. This is how we're going to make esters, amides, and ethers. So the first reaction we're going to look at is how would you make an ester. You need two functional groups for an ester. You need a carboxylic acid. That's how you're going to get the double bonded O. And you need an alcohol. Again, you saw this when we were looking at polymers together. This is going to make an ester plus water. Let's see it in action. So the OH will come off our carboxylic acid. The H will come off the alcohol. There's our water, HOH. And we're going to push the remaining ingredients together. So we have CH3, C double bond O, goes over to the O, CH2, CH3, plus the water that we just removed. Let's have a look at the amide. The amide is C double bond O with an N. So thinking about how I could get those two things, I'm going to need a carboxylic acid once again. That's going to get that double bonded O that I want. To get the nitrogen though, I need an amine here. Together they will produce my amide plus some water. Let's have a look at an example. So here's my example. It doesn't really matter the size of the chains. We can make all sorts of different amides here, but what happens is always the same. Again, between the two, I'll take away an H and an OH. I'll take the water away and push the remainder together. So CH3, CH2, C double bond O, and CH3, CH3, plus some water. Let's consider an ether. An ether, remember, is just an ROR, so an oxygen in between two carbon chains. What do you think we'd need to make this? We don't need a carboxylic acid because we don't need a double bonded O, but all we're going to use is actually two alcohols. That's all we need. So an alcohol, oops, let's just single that. Alcohol plus alcohol makes an ether plus water. So having a look, it doesn't matter who loses the H, who loses the OH, they're equivalent. We're going to take that water away and shove the remains together. So CH3, O, CH2, CH3 plus H2O. Our last type of reaction is combustion, and you did this in grade 11. We're basically taking any organic molecule, hydrocarbons, alcohols, anything, and the second ingredient is the more important one. When you see O2, that's going to be combustion. So don't confuse this with O square brackets. That's an oxidizing agent. Totally different reaction. Combustion is O2, oxygen gas. So pretty much any organic compound will burn pretty well here. And as soon as you see oxygen, you're just going to figure out what products. So complete combustion, you'll recall, is when we have just carbon dioxide and water vapor. We're going to assume that things are complete combustion unless it's otherwise stated. So if I say do a combustion reaction, I don't tell you what type, we're going to assume it's complete because usually we burn things in an environment that has plenty of oxygen. If I say partial, now we have less oxygen available and we generally make carbon monoxide instead of carbon dioxide. And if we have even less oxygen available, we're going to produce that carbon soot and water vapor. Let's have a look at an example. So I made this reactant specifically complicated looking and then added oxygen because I can't tell you how many times students look at this and they try to make some sort of crazy new product. But if I'm setting it on fire, I'm burning it all. If I don't say otherwise, again, you're assuming complete combustion, so you're making carbon dioxide and water vapor, and that is it. Doesn't matter how crazy of an ingredient I start with, I'm just setting it on fire and it's all gone, turned it into a gas. You don't have to balance it, so don't worry about that part, just show me the products. And that's it for now. Again, we'll start putting different reactions together as we go. And combustion of the 6, again, is sort of a single-step reaction. We would use it to get rid of something more often than not, but we generally don't use it in a set of steps because as soon as you set something on fire, you're kind of done with it.